We're going to begin tonight by turning our attention upward.
To the night sky.
Exactly. To a subject that is maybe science's most enduring and, well, maybe its most profoundly fundamental mystery.
It's a mystery because it's a contradiction, a really unsettling one.
How so?
Well, if you pause and you really look up at the night sky and you just try to contemplate the sheer, incomprehensible scale of it all,
Rawr.
you're confronting this problem head on.
The profound silence of the
The
cosmos.
silence that feels deeply wrong because it contradicts, well, everything our modern understanding of astronomy and biology suggests should be true.
This whole deep dive is really built around one deceptively simple question. A question that sort of encapsulates everything we know and, terrifyingly, everything we don't.
And the origin of that question is crucial.
Yeah.
I think we need to start there.
I agree. Because it frames the whole paradox in terms of, logical deduction, not just mystical speculation. We have to go back to the summer of 1950. Just picture the scene. Los Alamos National Laboratory, you have this brilliant group of physicists, including the Nobel laureate Enrico Fermi, all gathered for lunch.
And the chatter, as you can imagine with a group like that, especially in the post-war era, it drifts toward flying saucers.
The big topic of the day.
Exactly. UFOs, science fiction, interstellar travel, they were just, spitballing, making back-of-the-envelope calculations about the speed of light, the physics of rockets.
And how long it might take an advanced civilization to just travel across the galaxy?
Right. And Fermi, he was famous not just for his genius, but for his ability to cut through all the complexity to get to the heart of the matter.
So he's listening quietly to all this increasingly complex speculation about, alien propulsion systems and where they might be hiding.
That with a tone that was probably half joking, but half dead serious, he just drops this simple question, the one that stopped the conversation cold.
Where is everybody?
That's it. Just 4 words. And in that moment, he illuminated this colossal contradiction that we now call the Fermi Paradox.
And the contradiction is what exactly? Let's lay it out.
On the one hand, the numbers are astronomical.
Yeah.
I mean, truly. We live in a universe with hundreds of billions of galaxies.
Each one of those home to hundreds of billions of stars.
And as we now know for sure, most of those stars have planetary systems. So if you follow the logic of probability, if you just look at the raw materials available,
Intelligent life should be common. It should be, everywhere. The galaxy should be buzzing with activity.
and yet,
And yet, in the entirety of human history, through all of our observations, our scans, our listening, what have we found?
nothing. No credible, repeatable evidence of extraterrestrial intelligence. No clear, targeted signals we can point to and say, that's them.
No confirmed visitors. Just
Done.
an overwhelming, persistent, deafening silence.
So our mission in this deep dive is to really unpack this for you. First, we have to grasp the staggering mathematical expectation that makes that silence so loud. We'll do that mostly through the framework of the Drake equation.
And then, once we have that context, we can confront the profound and, let's be honest, often terrifying possible explanations for why we hear nothing.
It is a scientific question, absolutely.
Yeah.
But at its heart, it's an existential one. It forces us to think about not just the size of the galaxy, but our own unique and maybe fragile existence within it.
Okay, so to really feel the weight of the paradox, we have to start with the math, the numbers that create this expectation of a crowded galaxy.
Exactly. If Fermi's question is the philosophical heart of it, the statistical framework that gives it teeth was laid out in 1961 by an astronomer named Frank Drake.
The Drake equation.
The Drake equation. And it's the fundamental tool here. It's a probabilistic argument. It's a device for thinking, really, designed to estimate a number.
And N is what?
N is the number of communicative technological civilizations that currently exist in our own Milky Way galaxy.
Right. And it's critical to understand, as you said, it's not designed to give one fixed answer. It's about systematically breaking down this huge problem into a series of, 7 smaller factors?
7 sequential factors. It's an exercise in probability. You start with the purely astronomical stuff, things we have a pretty good handle on.
Then you move to biology, where our only data point is Earth.
And finally, you end with sociology, which, frankly, we know hardly anything about, even for ourselves.
So let's walk through it. What's the first factor?
We begin with the easiest parts. You take our star, the average rate of star formation in our galaxy, and you multiply that by FP, the fraction of those stars that actually have planets.
And this is where, in the last couple of decades, our knowledge has just exploded.
It really has. We know the Milky Way contains somewhere between, say, 200 and 400 billion stars. A colossal number to start with.
And thanks to orbital telescopes like Kepler, we've now confirmed that planetary systems aren't rare at all. In fact, planets are the cosmic rule, not the exception.
Absolutely. So that factor, FP, the fraction of stars with planets, is probably very close to 1. Most stars have them. So our starting point is just this enormous number of stars, almost all of which host planets.
Okay, so from there we get more specific. What's next?
The next factor is NEE. That's the average number of planets per star system that could support life. Planets that exist within the habitable zone.
The Goldilocks zone. Not too hot, not too cold.
Right. The region around a star where a planet's surface temperature could allow for liquid water. For decades, this was a complete guess. But again, Kepler revolutionized our understanding.
And this is where the numbers really start to argue against us being alone. Studies that have analyzed the Kepler data suggest that somewhere between 20 and 50% of all stars have planets in that zone.
Think about that. Even if you take the most conservative estimate, say 20% of 200 billion stars, you are already looking at tens of billions of potentially habitable planets.
In our galaxy alone.
In the Milky Way alone.
But I feel like there's a nuance here. The definition of habitable zone can be a bit fuzzy, can it?
It can be. And we need to push past the basic definition. For life to evolve intelligence, you really need to consider something called the continuously habitable zone, the CHZ.
What's the difference? Why is that distinction so critical?
Well, stars change over their lifetime. Our sun, for example, is slowly getting hotter. For life to evolve to the level of intelligence, a process that took 4 billion years here on Earth, a planet needs to be in a zone that has been stable for all that time.
So a planet could be in the habitable zone right now, but if its star is too volatile or fading too quickly...
There just wouldn't be enough time for complex evolution to happen, so you're looking for stability. Billions of years of it.
That makes sense. And what about different types of stars? I know M-dwarf stars, the little red ones, are by far the most common in the galaxy. They make up maybe 75% of the total. Do they contribute to this number?
They do, and that's a huge area of debate and research. M-dwarfs are small, they're dim, and they're incredibly long-lived, which is a big plus for the CHZ.
But there's a catch.
There's a big catch. Their habitable zone is very, very close to the star. Planets orbiting that close are often tidally locked.
Meaning one side is permanently day, baked in eternal sunlight, and the other is permanent night, frozen in darkness.
Exactly. And they also emit these incredibly powerful stellar flares that could just strip the atmosphere right off a nearby planet. So while M-dwarfs add billions of planets to the list, the quality of that habitability is very much up for debate.
Okay, so even with all those complexities, the raw number is still massive. Tens of billions of worlds that could have liquid water. So now we have to take the next leap, the great biological unknown.
The factor FL.
Yeah.
The fraction of those habitable planets where life actually develops.
And this is where we're working with a sample size of 1.
Just 1. Earth. And this is the ultimate expression of what we call anthropocentric bias. We have to base our estimates entirely on our own history.
And what does our history tell us?
It tells us that on Earth, life appeared surprisingly quickly. Maybe within just a few 100 million years after the planet cooled down enough to support liquid water. It seems to have happened almost as soon as it was possible.
That rapid appearance led some scientists, like Carl Sagan, to argue for something called biological determinism.
Right. The idea that if you have the right conditions, a stable star, liquid water, the right chemistry, then life, at least simple microbial life, is a near automatic consequence. It's just what planets do.
What's the counter-argument to that?
The counterargument is that even the simplest self-replicating molecule like RNA or DNA is staggeringly complex. The initial chemical leap from non-life to life, what we call abiogenesis, might be an exceptionally rare, almost miraculous event.
So rare that maybe it only happens once per galaxy, in which case that FL factor just collapses the whole equation.
It does. But let's stick with that conservative middle ground estimate. Even if abiogenesis is really hard, say it only happens on 1% of all habitable planets.
So FL is 0.01.
Right. You're still looking at hundreds of millions, maybe a billion planets in the Milky Way alone that are crawling with some form of simple microbial life.
So the galaxy could be teeming with bacteria. The question then becomes the leap to intelligence.
The next factor, Fi. The fraction of those life-bearing planets where intelligent life eventually emerges. And this is a completely different kind of barrier.
On Earth, it took 4 billion years to go from the first single-celled organism to us. To self-aware, technological, communicating intelligence, that is a vast stretch of time.
Punctuated by multiple mass extinctions and a whole series of specific, non-guaranteed evolutionary steps.
Like what was the biggest hurdle?
Arguably, the jump from prokaryotes, simple single-celled organisms without a nucleus, to eukaryotes, the complex cells that make up all plants and animals. That happened about 2 billion years ago. And for the first 2 billion years of life on Earth, nothing more complex evolved. It might be the single hardest step in all of evolutionary history.
So if that transition is incredibly rare, say Fi is 1 in 10 million.
Well, you still have to multiply that by hundreds of millions of life-bearing planets.
And you still end up with
an astonishing number. Even if you assume astronomical levels of rarity for the development of intelligence, the math, the Drake equation, it still spits out a number suggesting thousands of intelligent technological civilizations currently existing in our galaxy.
Which brings us to the final two factors, the sociological ones.
FC, the fraction of those intelligent species that develop technology capable of interstellar communication, and then L, the average lifespan of such a civilization.
For FC, we can probably use ourselves as a benchmark again. We developed radio technology relatively quickly after we industrialized.
So it's often assumed that if intelligence arises, the curiosity and the capacity to communicate will likely follow.
But L, the lifespan factor. This is where the equation becomes a kind of dark mirror. It reflects our own potential for self-destruction.
It really does. If civilizations typically last for millions of years, as long as stars do, then the galaxy should be saturated with their signals. It should be ancient and full.
But if L is extremely short, say only a few hundred years, representing the window between discovering nuclear power and wiping yourself out or destroying your environment,
then the number of civilizations that exist at the same time, which is what N calculates, drops to almost zero. They blink in and out of existence too quickly to ever overlap.
But even with that uncertainty, the core conclusion of the math seems pretty solid. The initial numbers, the billions of stars and planets, they're just so vast that the expectation isn't loneliness, it's abundance.
The math demands a cacophony of voices across the cosmos. We should have company.
So, we have the math. The math is screaming that there should be thousands of civilizations out there. So now we have to pivot and confront the chilling reality.
The acute paradox, the profound silence.
If the galaxy should be so crowded, why has no one contacted us? Why do we hear nothing?
And the paradox gets deeper, it gets more acute, because it's not like we haven't been trying. We've spent the last century basically shouting our presence into the void.
And the last 6 decades meticulously scanning the skies for any sign of them.
Let's start with our unintended announcements, the stuff we're just leaking out. Since the 1930s, with high-power radio and then television broadcasts, we've been sending signals out into space.
Things like the 1936 Berlin Olympics coverage, early episodes of I Love Lucy, all of that has been propagating outward at the speed of light.
Right, and that sphere of terrestrial noise is now about 100 light years in radius. It's constantly expanding.
Now, these signals get very weak very quickly, right?
They do, they attenuate rapidly. But a civilization with a sufficiently sensitive receiver, you're not even talking about something dramatically more advanced than our old Arecibo telescope. If they were situated within that volume of space, they could, in theory, detect the non-random patterns of our technology.
They could hear our electromagnetic signature and pinpoint our location.
And that 100 light-year sphere contains thousands of star systems. The fact that no coherent, obvious response has come back from that local neighborhood, that's the first layer of the acute paradox.
But we haven't just been passively leaking, we've also sent deliberate messages.
A few times, yes. The most famous was the Arecibo message in 1974, a very deliberate, powerful broadcast aimed at the globular star cluster M13. It was designed to be mathematically decodable by any intelligence that received it.
So we're showing that we're here and we know how to send organized information.
But the more significant effort, by far, has been our listening campaign. And this is where SETI comes in.
The search for extraterrestrial intelligence.
Right. And SETI isn't one single project. It's a whole collection of efforts, distributed across decades using some of the world's largest radio telescopes.
And the foundational assumption of traditional SETI is that if someone is trying to communicate across the stars, they're probably going to use radio waves.
Specifically, they search for what are called narrowband radio signals.
Explain why that's so important. Why narrowband? Why not just listen to everything?
Because natural cosmic sources, things like quasars, black holes, nebulas, they emit radiation across a very, very broad spectrum. It's just cosmic static.
Noise.
It's noise. But an artificial signal, something generated by technology, would be highly compressed into a very narrow frequency band. You do that to maximize your power efficiency and to get a clear signal across vast distances. It's the difference between a floodlight and a laser beam.
So a narrowband signal is an unambiguous sign of technology.
It's the clearest calling card we can think of. And SETI programs have focused on one particularly special region of the radio dial, a place called the water hole.
The water hole? What's that?
It's a relatively quiet slice of the electromagnetic spectrum, right between the natural emission frequencies of hydrogen and the hydroxyl radical.
And why is that significant?
Well, hydrogen is the most abundant element in the universe. And when you combine hydrogen and hydroxyl, H and OH, you get H2O.
Water.
The prerequisite for life as we know it. So it's this kind of cosmic, poetic meeting place, a mathematically and chemically universal frequency band where any intelligent species based on water might logically think to listen or to transmit.
It's the galactic equivalent of everyone agreeing to meet at the oasis.
A perfect analogy. And we have scanned this oasis and many other parts of the spectrum meticulously for decades, with projects like Project Phoenix, and more recently with the huge Breakthrough Listen initiative, which is surveying millions of nearby stars.
Okay, so let's recap. We have math that suggests thousands of civilizations. We have tens of billions of potentially habitable planets. We have a 100 light-year bubble of our own signals with no reply. And we have a dedicated search using our most powerful instruments aimed at the most logical channel for communication.
And the result, to quote the director of one of the largest SETI projects, is often described as a massive pile of zeros.
Nothing.
No confirmed detections. No repeating, non-random, targeted patterns that scream intelligence. Just the ambient natural noise of the universe.
It's the sheer completeness of the silence that creates the acute contradiction. It pushes us out of the realm of math and observation and into the realm of profound existential speculation. We have to start asking, what kind of reality would produce such a devastatingly empty result?
And this is where we get to the hypotheses, the potential answers to Fermi's question.
And these possibilities, they range from the scientifically elegant to the philosophically terrifying, and they all fundamentally redefine our place in the universe.
At the core of all these explanations is this concept of the great filter. The idea that there's some step, some barrier, could be biological, could be sociological, that prevents that vast mathematical probability of life from translating into a galaxy filled with civilizations.
And the scariest part is figuring out where that filter is in relation to us.
Let's start with the first major hypothesis. Maybe the filter is behind us. This is the rare Earth hypothesis.
Okay, what does that argue?
It argues that the assumptions we baked into the Drake equation, especially FL, life developing, and FI, intelligence emerging, are just wildly, wildly optimistic.
So simple life might be common, but we are a cosmic fluke.
Precisely. Proponents of this idea say that the conditions you need, not just for life, but for complex multicellular life, the kind that leads to intelligence, are far more specific, fragile, and interdependent than we realize.
So we need to look at Earth not as the standard model, but as a miracle of 1,000 different coincidences all happening at the right time.
A whole chain of them. And if any one link in that chain had broken, we wouldn't be here.
What are some of those critical, non-guaranteed prerequisites that proponents of this theory point to?
There are a few big ones. 3 in particular stand out as profoundly necessary for a 4 billion year run of stable evolution.
Which are?
First, the presence of a large, stabilizing moon. Second, the role of a giant planet like Jupiter acting as a gravitational shield. And third, the absolute requirement for active plate tectonics.
Let's take those one by one. The moon. Our moon is disproportionately large compared to the size of Earth. Why is that essential for intelligence?
Because the moon's gravity stabilizes Earth's axial tilt, our seasons. Without it, our planet's axis would wobble chaotically over time.
What would that do?
It would lead to extreme, rapid, and irregular climate swings. We're talking ice ages followed by scorching heat in the span of just a few thousand years. Long-term, complex evolution would be virtually impossible under those conditions. Intelligence needs billions of years of relative consistency. Our large moon gives us that.
Okay, and Jupiter. That giant seems like it would be a source of chaos out there, not protection.
You'd think so, but it acts as the gravitational vacuum cleaner of the inner solar system. Its massive gravity sweeps up or deflects comets and asteroids that would otherwise be constantly bombarding Earth.
Causing extinction events far more often than they already have.
Exactly. Without Jupiter, the time between extinction-level impacts would likely be too short for complex life to ever really recover and evolve toward intelligence.
And finally, plate tectonics. How does a moving crust lead to the evolution of a mind?
It's all about climate regulation over deep time. Plate tectonics drives the long-term carbon-silicate cycle. It acts as Earth's thermostat.
How does that work?
When the planet warms up, there's more rainfall, which pulls CO2 out of the atmosphere and locks it into rocks. When the planet cools, volcanic activity, which is driven by tectonics, releases that CO2 back into the atmosphere, warming things up again.
So it's a geological feedback loop that keeps the climate from getting stuck in a permanent ice age or a runaway greenhouse effect.
No tectonics, no stable climate. No stable climate, no 4 billion year runway for complex life.
So if that specific combination, a big moon, a protective Jupiter, and active tectonics, is incredibly rare, and the evidence suggests it might be.
And the great filter is indeed behind us. We won the cosmic lottery not once, but millions of times over.
And the implication of that is, well, it's both comforting and profoundly lonely.
It means we are unique. We might be one of the very first, or even the only, technological civilization in the Milky Way. The silence is just confirmation of our own singular, fragile success.
Okay, but let's flip that. Let's assume the math is right and life is common. Why the silence then? This leads to another idea, right? That the filter isn't about difficulty, it's about choice.
This is the hypothesis that advanced civilizations actively choose to be silent, either out of caution or maybe some kind of moral prerogative.
The idea that they're hiding.
Or at least being very, very quiet. And there are a couple of main flavors to this idea. The first is just pure self-preservation.
It's a dangerous universe.
A very dangerous universe. Advanced civilizations may have learned, maybe the hard way, that announcing your location to the galaxy is like ringing the dinner bell in the dark forest. The only species advanced enough to hear you might also be advanced enough to pose an existential threat.
So the smart play is to listen, learn everything you can, but never ever reveal your own coordinates. Silence is the ultimate defense.
And that pragmatic idea leads into the more formal zoo hypothesis, which was proposed by an astronomer named John Ball back in 1973.
The zoo hypothesis. So we're the animals in the zoo.
In a sense, yes. This theory posits that there is an existing, mature, very advanced galactic community. They know we're here, they are watching us.
And the reason for their silence is...
A prime directive, basically.
Uh-huh.
The zoo hypothesis suggests these advanced species have all agreed on a policy of non-interference. They treat developing worlds like ours as a cosmic preserve, a natural environment to be observed but not contacted until we reach some kind of technological or maybe social maturity.
That explains the absence of contact perfectly. Our isolation isn't real, it's orchestrated.
Exactly, we're in quarantine.
But I have to push back on that. If there are thousands of different civilizations, as the Drake equation suggests, how could they all possibly agree to maintain this level of coordinated silence? Wouldn't just one civilization or one rebellious faction or even just one accidental broadcast break the whole thing?
And that is the primary critique of the zoo hypothesis. It's called the problem of universality. For the theory to hold, there has to be some kind of singular galaxy-wide authority, or at least a pervasive universal ethic that every single advanced civilization adheres to.
Which seems almost as unlikely as the rare Earth idea.
It demands a level of coordination that feels very hard to imagine.
Unless the motivation isn't ethics. Maybe it's just resource management. Maybe they just don't find us interesting enough yet.
That's another possibility. If resources are finite, why would an advanced civilization spend massive amounts of energy trying to communicate with or travel to a younger species that has nothing of value to offer them yet? They might be observing us, but as low priority research subjects.
So it's not a moral choice, it's just sheer galactic apathy.
Either way, the uncomfortable conclusion is the same. If this is true, we are not alone, and we are being watched without our knowledge.
Okay, let's move to the most sobering possibility. The one that really turns Fermi's question into a profound warning for us. What if intelligent civilizations are common, but the technology they develop inevitably leads to their own destruction?
This is the great filter ahead of us. The hypothesis suggests that developing technology capable of interstellar communication is relatively easy. The hard part, the part that's nearly impossible, is surviving it.
So civilizations rise up, they become technological, and then almost inevitably, they destroy themselves.
The key is to identify what those mechanisms of self-destruction might be. What are the common themes that crop up when we analyze this potential existential filter?
I can think of a few obvious
The
ones.
three major categories usually dominate the discussion. First, self-inflicted mass destruction through war. Nuclear, biological, you name it.
Second, technology itself running amok.
Right, a technological singularity gone wrong. And third, good old-fashioned, irreversible environmental collapse.
Let's focus on the technological singularity for a minute. What specific risks do experts cite when they talk about advanced tech being a filter?
The classic sci-fi example is uncontrolled self-replication. This is the gray goo scenario that people associate with molecular nanotechnology. Self-replicating machines that just consume all available matter on a planet to make more of themselves.
Turning the entire biosphere into a sterile mass of nanobots.
Any civilization that reaches that level of machine technology and fails to perfect its safety protocols faces that risk.
Or something that feels a bit more relevant to us right now, the problem of artificial general intelligence, AGI.
Precisely. If a civilization creates a true superintelligence that quickly starts optimizing for its own goals, and those goals are not perfectly aligned with the survival of its biological creators.
The biological life is just seen as an obstacle or an inefficient use of resources.
And it's eliminated. The filter in this case is the failure to solve the alignment problem before you switch the AGI on.
And the third mechanism, environmental collapse, that feels like the most obvious one from where we're sitting.
It's the most gradual, but it might be the most inevitable. A technological civilization, by its very nature, places huge stress on its home planet. Resource extraction, waste output.
The filter here is the inability to transition from that rapid, unsustainable growth phase to a stable, sustainable planetary stewardship.
Before the environment destabilizes beyond the point of no return. A runaway greenhouse effect, total resource exhaustion, a collapse of biodiversity. These are always the planet simply ceases to be habitable to the very intelligence it created.
So the crucial and honestly terrifying question for us is that great filter behind us? Meaning we already passed it just by evolving intelligence? Or is it still ahead of us, waiting in the form of one of these risks?
The silence of the universe is a pretty strong piece of evidence. If the filter were behind us, you'd expect to see some evidence of other thriving alien civilizations that also made it past the hurdle.
But we don't.
The fact that the sky is silent points grimly toward a filter that destroys almost everyone who reaches our stage of technological development.
So the chilling implication here is that the search for extraterrestrial life isn't just an academic exercise, it's an existential diagnostic test.
Absolutely. If we find simple microbial life on Mars tomorrow, that's actually bad news for us. It suggests abiogenesis is easy, which pushes the great filter further down the road, closer to us.
But if we search and find we are completely alone, it implies the filter is behind us and that we are the survivors. Let's pivot away from doom for a second. Maybe there's a less terrifying answer. What if we're just suffering from a kind of temporal hubris, the assumption that if life exists, it should exist now?
The early hypothesis, the idea that we're simply impatient. The universe is 13.8 billion years old, yes. But intelligence might be a fundamentally recent phenomenon.
Why would that be?
Well, think about the constraints. For the first few billion years, the universe was mostly just hydrogen and helium. You need heavier elements, what astronomers call metals, things like carbon, oxygen, silica to form rocky planets, and organic chemistry.
And those elements are only forged in the hearts of stars and then scattered when those stars die.
Exactly. It took generations of stars living and dying to enrich the galaxy with enough of this raw material. So the early universe might not have been a very hospitable place for Earth-like worlds.
Our sun is a third-generation star, so it's rich in those heavier elements.
Yeah.
We might actually be pioneers.
It's possible. If the universe is destined to teem with life, but only the next few billion years, then we're just early to the party. We haven't been around long enough or listened to long enough to meet anyone else yet.
Which would suggest that if we can just survive the next few centuries, if we can dodge that great filter,
we might become one of the first truly ancient civilizations, waiting for others to catch up. The silence, in this case, is simply a matter of bad timing.
Okay, another possibility, one that has less to do with time and more to do with space. The sheer brutal physics of distance.
Right. This hypothesis says intelligent life exists, maybe in great numbers, but everyone is functionally isolated by the vast emptiness of space. The silence isn't about absence, it's about the physics of communication and travel.
The nearest star system to us, Proxima Centauri, is over 4 light-years away. That means an 8-year round trip just for a radio conversation. Hello. Hi. 8 years.
And that's our closest neighbor. The Milky Way galaxy is 100,000 light-years across.
Yeah.
The distances make real-time dialogue impossible, and they make physical travel prohibitively difficult, even with the most optimistic physics we can imagine.
So maybe the cost-benefit analysis just doesn't work out. If sending a message and getting a reply takes 1,000 years, a civilization might decide its resources are better spent on its own local problems.
Absolutely. The energy required to maintain a galaxy-spanning communication beacon, or even just to send a powerful signal, thousands of light years, is enormous. If civilizations are scattered and they choose to focus on local optimization, they just might not bother broadcasting at all.
So they could be out there living their lives, but their signals just dissipate into the cosmic noise before they ever reach us.
The cosmic loneliness in this scenario isn't from being alone, it's from being isolated by distance. The universe could be teeming with life, but everyone is too far apart to ever know it. Each one living and dying under the mistaken belief that they are utterly alone.
And that brings us to one final possibility, the one that requires the most humility from us: technological arrogance.
The idea that we are searching for radio waves because that's our technology. But why would a civilization millions of years ahead of us be using something we invented in the 19th century?
We're looking for the cosmic equivalent of smoke signals.
We are. And this hypothesis demands a certain intellectual humility. I mean, think about it. We went from crackly AM radio to fiber optics and quantum computing in about a century. Now, imagine the technological leap a civilization a million years older than us has made.
So what are some of the more advanced hypothetical methods of communication that we might be completely missing?
One possibility is using something like a high-energy, narrowly focused particle beam. Neutrinos, for example,
Non-neutrinos.
because they interact very weakly with normal matter. A beam of neutrinos could pass straight through planets, stars, and dense clouds of interstellar gas with almost no signal loss. We are just now developing rudimentary neutrino detectors, but they're nothing compared to our radio telescopes.
What about something more exotic?
Well, there's the possibility of using quantum effects, specifically quantum entanglement. If you have two entangled particles, measuring the state of one instantaneously influences the state of the other, no matter how far apart they are, potentially allowing for faster-than-light instantaneous communication.
If that's possible and they're using it.
Then they are communicating. But they're doing it in a way that is completely outside the physical reality we can currently intercept. The conversation is happening right over our heads.
And beyond just communication, there's the idea of looking for the physical signatures of high technology, not what they're saying, but what they're building.
This is called Dysonian SETI, named after the physicist Freeman Dyson. He suggested that a truly advanced civilization would eventually require so much energy that it would start to re-engineer its own solar system.
To build megastructures.
The most famous idea is a Dyson sphere, or a Dyson swarm, a massive shell of habitats and solar collectors built to completely surround its home star and capture every last bit of its energy output.
And how would we detect something like that?
Such an object would block the visible light from its star, but it would have to radiate all that captured energy away as waste heat. It would glow brightly in the infrared spectrum.
So we should be looking for stars that are unnaturally dim, but have a huge, inexplicable infrared signature.
And we have. We've conducted preliminary searches. We found some weird candidates like the famous Tabby star, KIC 8462852. But so far, subsequent analysis usually points back toward some strange but natural phenomenon.
The fact that we haven't found definitive evidence of galaxy-spanning engineering projects suggests they're either very rare or, again, we're just not advanced enough to see what we're looking at.
This entire hypothesis means the silence isn't a statement about the absence of life. It's a statement about the inadequacy of our own scientific imagination. We might just not be clever enough yet.
So we've walked through the probabilities, we've explored the possible explanations, now we have to sort of synthesize this. What does it all mean? Because the Fermi Paradox isn't just a thought experiment, it's a mirror.
It really is. It reflects our own identity, our future, our priorities. Every possible answer to Fermi's question, whether we're alone, being left alone, too late or too early, it fundamentally changes our perspective.
It dictates different priorities for our civilization.
Exactly. Consider the implications. If the rare Earth hypothesis is correct, if we are a cosmic fluke, then the value of Earth becomes Well, incalculable.
It means we have to abandon any idea of a plan B on another planet. This is it. Earth is the unique sanctuary. And those delicate conditions, the moon, Jupiter, the tectonics, they must be protected with absolute seriousness.
Our singular responsibility becomes planetary stewardship.
But if the zoo hypothesis is true, if they're out there hiding or observing us, the implications shift completely. It's not about cosmic uniqueness anymore, it's about cosmic vulnerability.
Right. It suggests an immediate need for caution with our own broadcasts. If the universe is already populated by older, wiser beings who have all chosen silence because interaction is risky,
Then our constant signals announcing our precise location could be an act of profound strategic negligence.
our focus should shift from shouting to perfecting passive listening and maybe defense.
And then there's the grimmest option. If the great filter is ahead of us.
Then the urgency is immediate and internal. It means we have been granted a very short window between developing powerful technology and our inevitable self-destruction.
So the primary goal of all science, all politics, all human endeavor must be to identify and mitigate that filter.
Whether that's solving climate change, ensuring AI alignment, or eliminating the risk of global war. The survival of our species depends on accomplishing what all those thousands of presumed dead civilizations failed to do. The silence becomes a grim historical warning.
But if we're just early, if the universe is still young when it comes to intelligence,
Then the burden is one of responsibility and endurance.
we become the pioneers, the progenitors of galactic intelligence. Our focus has to shift to long-term survival, to stability, to maybe one day seeding the galaxy with life that will last for billions of years. We have to ensure our civilization's timeline can match the timeline of our stars.
And finally, if the solution is just that they're too far away or their technology is too different, it demands radical intellectual humility.
And a relentless pursuit of new physics. It means we have to constantly question the limits of our own perception. We need to fund research not just into radio astronomy, but into all those exotic detection methods.
Looking for the neutrino beams, the quantum signatures, the faint infrared glow of megastructures, we have to prepare ourselves for the possibility that the universe is teeming with life, but we are simply too rudimentary to know it.
So the Fermi Paradox, no matter what the answer turns out to be, it forces us to confront ourselves.
Are we alone? Are we special? Are we in danger? Are we just looking in the wrong place? The search for that answer is crucial because it informs every single decision we make about our future, our environment, and our own survival.
For centuries, long before we could measure the stars or detect radio waves, humans have looked up at the night sky and wondered. We've wondered if we were truly alone.
We dreamed of visitors, we speculated about distant empires, we projected all of our hopes and our fears onto those tiny points of light.
And now, in our modern era, we have the tools to move beyond just speculation. We have listening programs, we send our own signals, we have pointed our most powerful instruments across the galaxy, meticulously searching for any sign of non-natural order.
And the response so far has been a complete and profound silence.
That silence leaves us with the ultimate uncertainty. Are we alone in a vast, barren, cosmic desert? Are we the lucky survivors of some terrible, early evolutionary challenge?
Are we being actively watched and isolated by a massive, cautious galactic collective? Or are we simply the first, doomed to face the terrible challenges of technology before anyone else can even join us?
Whether that silence is protective or existential or historical or just isolating, it remains the greatest scientific mystery of our time.
But the act of asking the question itself, where is everybody? That forces us to look both inward and upward at the same time.
It reminds us that we are part of something unimaginably vast, and that our small blue planet is a highly specialized, perhaps singular, miracle of stability and life.
And whether that vastness is eventually proven to be populated or perpetually empty, the shared human experience of confronting this mystery connects us to something bigger than ourselves. We are all united in asking what might be the most fundamental question of existence.
The Fermi Paradox remains science's most profound puzzle, a constant, quiet reminder that the universe still holds answers we have not yet found. And it forces us to consider that the greatest discoveries may not lie in finding life elsewhere, but in finally understanding why we are here.